All right, let's get started, everybody. Okay, so welcome back after the celebration last week. I'm still working on grading those, but my goal is to have those graded probably either by the end of this week or early next, mainly because I don't want to have 2 stacks of exams on my desk, and I know your analysis professor has an exam on Monday. In terms of attendance, everybody was counted present for the exam, so you got that credit as well. I didn't take a QR code for the exam, but I just want to put that out there. Homework 3 and Lab 4 were both due today, so they obviously have not been graded. So that'll be something I work on this week. In fact, this week for me is going to be chipping away at all the external or all the outstanding grading that needs to be done. It is not because of that. It is for a different reason. But I'm not giving you any homework this week in this class. So, but it's not because of that. It's for a different reason. I'm going to circle back to the lab today. I'm going to spend a little bit of time talking about that here in a bit. But I want to take a second and talk about the schedule in this class for the next few weeks, mainly because I want you to kind of understand what's going to be happening between now and the next exam. Okay, and so I put, if you go to the syllabus, I list the lecture topics and the lab topics, but I don't list when the assignments and whatnot are due, so I wanted to show you that. I think somebody used the expo marker here on the screen, so that's...
Why does that happen so often?
I don't know. I don't, so, but it's not me. I don't even have any, so. Okay. Let me pull this up real quick. So I know there's a lot going on here, but I want to sort of walk you through what's going on. So first off, we're in this week right here, and I'm not giving you any homework this week, okay? The next homework that I give you, I'm going to assign it not Thursday, but next Thursday. It's going to be due the following Thursday, and then I'm going to assign a homework here due this day, okay? So the next exam in terms of computations will largely follow 4 and 5 in terms of the homework assignments. This week is going to be very terminology and content heavy and not so much computationally heavy, because this week we're going to be talking about cement, Portland cement, and admixtures. And we'll get into the topic of concrete between then and when we're ready for the exam. So we're sort of in, so the reason why I don't have a homework assignment for you this week is because we're kind of in a weird spot where in lecture we're done with aggregates. Like we discussed aggregates, we're done with them, but we still have a lab to do with aggregates because, you know, it just takes a while to do some of these labs. So our lab today is going to be on fine aggregates. We're going to do shape and absorption. I'll talk about that here in a bit. So today and on Thursday, we're going to sort of fill in that time talking a little bit about Portland cement and admixtures for concrete. And so we might end class a little bit early so we can start this lab a little bit early today, and then we'll round out Thursday and maybe start to briefly discuss Portland cement concrete on Thursday. In terms of the labs moving forward, so just a couple housekeeping items. So today's lab could go quickly, it could take a little while. The absorption test can be a little bit touchy to do, and I'll show you some details on that here in a bit. Next week's lab is going to be our mortar lab. So what we're going to do is we're going to do what's called a VITAP penetration test. I'll talk a little bit about that today. And then we're going to cast our first set of samples for testing at a later date. So we're going to cast these mortar cubes, and then the next week in Lab 7, we're going to do a compressive test on those. So the idea is like this lab will take a little while. This one will probably be pretty quick because the samples will already be ready. We'll just demold them and start testing them, okay? Now, in terms of the labs, I am going to have a lab handout due each week, but some of them are going to be longer than others. So, for example, the Lab 7, where we do the mortar cube testing, you're basically just going to report your data and then make some comments, and then that's basically it. So there is that. Okay, what else? So this week we're going to discuss Portland's cement and admixtures. For the next couple weeks after that, we're going to be in the land of concrete. And really, the topic of Portland cement concrete is really sort of the star of the show, I would say, of this entire course. Because we discussed aggregates, we're discussing cement, we're discussing admixtures, really to feed into concrete. That's really like the star of the show of CE 321. So we're going to spend a fair amount of time on concrete. And one of the pinnacle things that we do in this class is what's called a mix design. Now, if you all have done any work on the concrete canoe, you probably kind of know what I mean already a little bit when we're talking about a mix design, but we're going to take that sort of step by step. So I'll show you some simplified design procedures for that, and then this is where it really gets interesting. So I'll spend a whole day just explaining the refined process for performing a mix design, and then we'll do a comprehensive example. The reason why I'm sort of showing all of this is because the refined design method for mix design is going to be a big star of the show on exam 2, and I've laid out this schedule to where you'll have done it a number of times before the exam. So it'll be something you're very familiar with. So we'll do it in class, it'll be part of the homework assignment, and you'll have to do a mix design for this lab. So by the time we take the exam, you'll have done this quite a bit, okay? All right, does that make sense? Bless you. Okay, so a couple other housekeeping items. So Thursday, October 9th, we do not have class because that's our October break, so we're not here together. Okay, on Tuesday, we're doing our exam review, and then we're having this lab. This lab is a long one, okay? I'm just going to go ahead and say it right off the bat. So much so that Lab 9, there's so much going on that Lab 8, Patrick and I are just going to do the lab in front of you, okay? And so this Lab 8 that you're going to turn in is basically you taking notes on the experiment that you're going to do the following week. Because you're going to have to mix up a big old batch of concrete. You're going to have to do a slump test, an air content test, a temperature test, and then cast all your cylinders and your beams. So there's a lot going on with Lab 9, and it is one of those labs, I'm telling you, that you could be here for a little while, okay? So I'm just putting that out there now, okay? So you'll take notes on what we do on this day, and then this day we get to work, okay? This is a messy day, so just saying. I mean, we're mixing up concrete, so just be aware of that, okay? What I'm going to do for this is sort of like the big lab in this class, for the concrete lab. We have 6 groups in the class. Each group is going to have a different mix, okay? And there's going to be one group in the class that has a really stiff mix of concrete. It's going to be a little bit difficult to mix up. There's going to be one group that has a really soupy mix of concrete, and then everything in between. And so why that's going to be relevant is the one lab report that everybody's going to do themselves is the concrete report. Instead of a group assignment, that's going to be an individual assignment. And you're not just going to assess your lab group's data, you're going to assess everybody's data. So that's, you're going to take your lab group's data and compare it to the rest of the class. So after this lab, we're going to have like 7-day testing, 14-day testing, 28-day testing, and we're going to be collecting this data throughout the rest of the semester, and you'll turn in this report probably before Thanksgiving break. So depending on the schedule, it'll either be before Thanksgiving break or a little bit right after. I'm shooting for before Thanksgiving break so that you all can turn in the report and not have to worry about this class while you're worrying about turkey. Okay? Does that sound good?
Yeah.
Okay. Any questions about the schedule and what's going to be happening over the next few days? A few lectures. Okay. And did everybody get the code? Okay. So let's talk about today's lab. Today's lab, what we're going to be doing are 2 things, and then we'll get into Portland cement and admixtures. So we're going to be doing 2 things today. One of them is the shape of fine aggregate. So if you remember the lab where we had like the pile of gravel and you had to classify how many were angular, subrarounded, rounded. In the gravel lab, you're able to, like, this is the number of particles that are flat, this is the number of particles that are round, and et cetera. We're doing this for sand, okay? That's not possible. Like, again, it's not possible to start counting them up. So what you're going to do for each sample is say, for this sample, we'll say 20% of it's angular, 30% of it is rounded, 15% of it is subangular, et cetera, right? And so you're going to do that through visual classification. So I'm saying that now that I don't want the class to sit there and try and count every little particle of sand. Please don't do that. You will be here for that. Will make a long lab. Don't do that. This is just a visual classification on the state of the sample that's been given. We've got 3 samples ready for you for visual classification, not 5. And if I'm correct, I believe that one of those samples is going to be somewhat unique. I'm going to sort of keep quiet as to what that is, but I think you'll get a kick out of it as to what the sample actually is. It depends on if Patrick selected that one or not. We talked about it. I think I'll let him make up his mind on that. Okay. All right, so there's 2 exercises today. One of them is the shape of fine aggregate, which is this. The other is absorption, okay? So if you remember, all right, how does an absorption lab work? Let's talk about the absorption lab that we did for gravel, okay? So for gravel, what we did is we found the moisture content for the gravel at saturated surface dry conditions, right? Now, saturated surface dry conditions are when the surface is dry, but all of the pores are filled with water, right? Is that right? That's what saturated surface dry is. And then we take the weight at the saturated surface dry condition, we take the weight once it's been oven dried, and then we can get the weight of the water over the weight of the solids, and that's our absorption, right? Okay? So that's exactly what we're doing here. The difference is, how do you identify when sand is saturated surface dry? It's a little bit easier for gravel because you can see the surface characteristics. You can't really see the surface characteristics for sand, okay? So the way that we're going to do that is we're going to follow a particular ASTM standard involving what's called a cone test, okay? Now I'm going to kind of show you real quickly what that is. Let me pause this. Okay, so, all right, so today what we're going to do is let's talk about safety real quick. I don't really think there's anything that's worth noting that we haven't already noted before in another lab in terms of, you know, like there's sand, so there's particles in the air, so be careful if you're handling sand with your safety glasses and all that jazz. We don't have anything particularly heavy in this lab. One thing I will mention is that one of the surfaces that we'll use, the non-absorbent surfaces, is a sort of a pane of glass. It's about yay thick, so just maybe be a little bit careful with that. But other than that, I think it should be a fairly straightforward lab in terms of safety and whatnot. Okay. Sound good? Okay. So this week, what we're going to do is talk about cement. Okay, cement and admixtures. Okay. So I want to talk about the properties of cement. I want to talk about how to produce cement, some of the reactions. Like I said, I might touch a little bit on the admixtures, but I'm probably going to try and spend most of my admixture discussion on Thursday, so we can start to ease into Portland cement concrete on Thursday. Okay, so the first thing that I want clear in this room is that cement is not concrete. Okay, I have, you know, if you're like walking, you know, down the road and you're walking on the sidewalk and you trip and fall, you don't hit the cement, you hit the concrete. Cement is an ingredient in concrete. Okay, concrete is a mixture of primarily 4 quantities. Well, 3 if you consider it just aggregate, but coarse aggregate, fine aggregate, cement, and water. Okay. So aggregate is an ingredient in concrete. Water is an ingredient in concrete. Cement is an ingredient in concrete. Okay? So cement has been in existence for about 200 years. It was patented in the 1820s, and the name Portland cement comes from the primary ingredient that was used to first manufacture it, which was limestone, and that came off of the cliffs of the Isle of Portland in England. I'll say this, I will probably try and keep terming it Portland cement, but there are, first of all, let me just say, there's oodles and oodles of different types and classes of cement, but Portland cement is so prevalent that a lot of times the terms cement and Portland cement, at least in civil engineering construction contexts, are pretty interchangeable. So if I say cement, more often than not, I mean Portland cement. What does cement do? Well, the chemical reaction between cement and water is basically the glue that bonds the aggregate together and forms concrete. It is the activating agent that turns this slurried mix of crushed up rocks and water into concrete. That's what it does. Okay? So a little bit of terminology, because I want to throw some things out there. So like I said, concrete is a mixture of gravel, sand, cement, and water. Okay? If I take that same mixture and I just eliminate the gravel and I mix water, sand, and cement, I get mortar. Okay? So mortar is it's essentially just a reduced aggregate concrete, but that's the stuff that we put between bricks and between masonry units, okay? So that's what mortar is. It's just concrete without the gravel, okay? And we can make cement paste by just taking cement and water and mixing it together. I'm going to pull up this YouTube video from How It's Made on some cement production, because I kind of want you to see that. I think that's kind of important. I didn't really do one for aggregates, because aggregates, I mean, it's really, for the most part, just crushed up rock. But there is a process in the production of cement that I thought is worth pointing out. In terms of the volume of the mix, we'll do computations that include both volumes and weights when we start looking at our refined mix design process. But Portland cement in a concrete is probably around 7 to 15% of the mix. The biggest component of the mix by volume in concrete are the aggregates, which will take up anywhere from 60 to 75% of your mix, depending upon your goal. The specific gravity of Portland cement, because it is a manufactured product, is something that you can sort of take to the bank, and it is 3.15. And that's consistent for all different types of cement, because we have like type 1, type 2, type 3, et cetera. The one thing about cement is that because the bulk unit weight is a function of volume, and there's all sorts of different air voids that might be present in a given sample of cement, we don't really measure cement by volume. We typically measure it by weight, okay? I'll say a couple things about the process, and then I'm going to pull up this video. But we basically take two main ingredients that we call calcareous materials and argillaceous materials. So that can typically involve limestone along with clay. The calcareous materials can also include chalk, and even can include organic compounds like oyster shells. And then we take clay, shale, maybe blast furnace slag. Essentially what we're doing is combining those up, grinding them up, cooking them up to a really, really, really hot temperature to generate that chemical reaction that turns the ingredients together into clinker, and then process that a little bit further into cement. Okay, I'm going to turn it over to the How It's Made folks, because I think that they show the process a lot better than I could. So I'm going to pause this and pull that up. So. Okay. All right. So I don't want this. I'll say this. I'm going to go through the key, I think, aspects of what I think is important for you all as civil engineers. I'll say a little bit about the chemistry. I don't want to go too far down the rabbit hole on that. But a couple things I'll say. So number one, I think it's kind of interesting when you review the process for manufacturing cement. In terms of the manufacturing process, the actual chemistry is something that happens really just in 1 or 2 steps, but there's so much involved getting the particles to the right size. There's a lot of processing of taking materials, turning it into this gradation, and then turning it into that gradation, and then you produce the clinker, and then you grind it again. And there's a lot of QA/QC in getting the particles into the appropriate size. And there are reasons for that. Now, what are the steps? I mean, again, we just sort of saw this, but we basically crush our materials and run them through a grinding mill. We run them through a kiln, which that gets really, really hot, up to around 3,000 degrees Fahrenheit, to produce clinker, and then we grind that clinker with the gypsum to produce a fine powder, which is Portland cement. Obviously, I think so a couple things. Obviously, I think that you need to keep cement dry. Cement will draw out moisture from the air, and then it will start to react, which is something we don't want. We typically transport cement in sacks, and it's sort of a standard weight that a 94-pound sack is about a cubic feet of loose cement. And so now it's loose cement, so this this ratio doesn't quite go to a specific gravity of 3.15, but again, the material parameter, we can take 94 pounds for 1 cubic feet. We can take that pretty standard. Keep in mind this 94-pound sack is also going to have a lot of air in it too, which is why the math's a little different. So there is, so again, I'm going to sort of very briefly go through the the process. I don't really want this to go too far down the rabbit hole into a chemistry side of things, but a chemical reaction obviously takes place in the kiln that produces the clinker, and there are several compounds that get generated that are basically combinations of calcium, silicon, oxygen, and some iron and aluminum and whatnot in there. These are the 4 primary compounds that get generated in the kiln. There are some other compounds that get produced in smaller quantities, but they can be very important in terms of the overall process in producing concrete. One thing that I think that I already said this, but I'll sort of restate it, that was hopefully came across in the video that we watched on producing concrete or producing cement, is that a lot of effort went into generating the powder to a specific fineness, okay? And the particle size of cement particles is very, very important, okay? The reason why is because the more fine your particles, it controls the rate of hydration. In other words, if I have like particle A, which is this big, and I have 2 particle Bs, which comprise the same weight, well, they have a bigger surface area. The more surface area that the cement can come into contact with the water, you can get a more controlled rate of hydration. But you can't, on the flip side, you don't want the particles to get too fine, because then they'll react with the water too quickly and the concrete will set faster. So there's a very specific control there, okay? Now your particle diameters are, for cement, are really tiny. So for example, most of the particles, if we were to do the math, would pass like the number 325 sieve. So I mean, they're pretty tiny particles. Just to like give you some numbers to put this in perspective, if you had a kilogram of Portland cement, so just a little bit, that's like 7 trillion particles. That's a lot, So so this is sort of what I was getting at. When I was saying there's a lot of effort in the production of cement of just getting it to the right particle size and whatnot. How many of you have ever worked with concrete? Have you ever set concrete? It's hot, isn't it? It produces heat, right? So one of the things that you will get in a reaction between cement and water is the production of heat, okay? And what ends up happening is, so there's several chemical reactions that occur during cement hydration. So for example, what happens when you take tricalcium silicate plus water, or tricalcium aluminate plus water, or gypsum, and so on and so forth. But it's the tricalcium aluminate plus the water, that's the one that generates the heat, okay? And that is one of the things that we have to watch for whenever we're producing concrete, is controlling that heat generation, especially in production of mass concrete elements, or any elements where the element that we're casting is really, really big. Just something as simple as the right cement to use in order to control that that heat that's generated. It is pretty important, because if you have uncontrolled or differential heat in your element, you can get defects in your element without even having done anything. It's just the heat changes and whatnot. Okay, let's talk about what happens when you start to react the cement with the water. So the development of the solid structure between cement and water, it begins the moment that water comes into contact with the cement. If you're talking about cement paste, just cement and water, it'll be workable for about 45 minutes, and then it's going to start to solidify. And it'll solidify within about 2 to 4 hours, and then it's pretty much like not workable, okay? So if you've ever worked with concrete, the moment that they start mixing it, you're on a timer, right? So, and everybody who's ever worked with concrete should know that, okay? Now, what happens is that those particles start to form bonds, and they form bonds by hydrating, okay? And concrete or cement, I guess I should just, since I'm talking about cement right now, those particles will continue to hydrate and continue to form those bonds. But what ends up happening is, so if we start looking at regular old, let's say everyday concrete, and we're looking at its compressive strength. So this is looking at concrete, it's not just looking at the cement, although like that's what this curve is. This curve is looking at just the cement and whatnot. What you find is that over the life of the specimen, and when I say life, I mean from the moment that water comes into contact from then on, you will get varying degrees of behavior. So what we'll do in the lab is, for example, we'll cast a mortar cube, and then 7 days later we'll test it. When we do our concrete testing, we'll do 7, 14, and 28 days. What you find when you start tracking compressive stress as a function of age is once you get past 28 days, things start to settle a good bit. That's not to say that the strength doesn't change. It does. I mean, if I take a cylinder after 28 days and test another cylinder after 28 years, I'm going to get different answers. I am. But your rate change after 28 days really starts to flatten out a little bit. So a lot of times what you'll find in performance specifications, things like the bridge code, things like ACI 318 when you're doing reinforced concrete design, is that a lot of the design equations that we use, a lot of the methods that we use to design concrete elements, we rely on a 28-day compressive strength. And why 28 days? Because again, after 28 days, the rate at which compressive strength changes drops quite a bit. Okay, that's why in here we'll do 7, 14, and 28. Okay, let's talk about the fifth ingredient in concrete. And sometimes it's wanted, sometimes it's not. And what do I mean by the fifth ingredient? Well, Dr. Mike, didn't you say there was gravel, sand, cement, and water that goes into concrete? Yeah, there is a fifth ingredient, though, and that fifth ingredient is air. Okay, air can be in your mix. Okay, there are a number of reasons for voids in hydrated cement. Some of them can be on purpose, things like entrained air. Some of them can be not on purpose. So, for example, if it was poorly placed or poorly consolidated, that can generate voids. And sometimes you'll get voids just because of the molecular structure of the cement and water reaction. Those voids have very significant impacts on the behavior of concrete. They can affect its strength, its durability, etc. Now, sometimes those voids are desired. Okay. So, for example, how many of you have ever worked on a DOH project, summer had a DOH internship? Did the term air entrainer ever pop up, or air entrained concrete? Anybody ever mention that? You're shaking your head, yes. So an air entrained concrete is when we purposefully generate the mix. We insert what's called an air entrainer, and it adds bubbles into the mix. Okay, those bubbles are a good thing. Okay, they're by design because they sort of act as like a ball bearing. And allow a little bit of movement of within the structure of the concrete during freeze-thaw cycles, which is definitely going to happen in outdoor placements of concrete, right? It's going to get hot, it's going to get cold, and so it gives you a little bit of wiggle room. It's appropriate for those types of applications. Other applications it may not be appropriate, okay? So it just depends on what you're doing. Okay. I think I already said all of this, so I'll move past this. What I want to focus on here is that I will, as a result of this fifth ingredient, air, I will use specific verbiage. Okay, I will use either entrapped air or entrained air. Entrained air is by design. Okay, that's on purpose. Okay, that's produced by including an admixture. We'll talk about admixtures on Thursday. And it's a good thing for concrete, particularly concrete that's going to be placed in exterior situations or situations that are subjected to freeze-thaw cycles. Entrapped voids, That's not good, okay? Entrapped voids are whoopsies, okay? Those are what happened when the concrete was handled poorly, it was placed poorly, it decreases strength, it increases permeability, which is really bad for external applications. What do we put on the top of the road in February in the great state of West Virginia?
Salt.
Salt. And we don't like that stuff to permeate into the concrete because if that hits the rebar rusts, metal rusts, it expands. That's no good. So that's a bad thing. So entrapped voids are a bad thing, and trained air is a good thing. And trained air, you know, again, we're talking about microbubbles here. Okay. A little bit on terminology, and this is the VICAP penetration test that we're going to do in lab next week. But if I use the term setting, so setting refers to the stiffening of the cement paste or the transition from what we would call a plastic state to a solid state. So setting is just it becoming solid, okay? Hardening is it gaining strength over the life of the use of the element. So the setting of cement paste or the setting of concrete happens within a few hours of your mix. Hardening happens over life, okay? I'm going to very briefly mention this VICAP penetration. We're going to talk about it a lot more next week, but one of the ways that you can measure the stiffness of cement paste is to perform a calibrated penetration test, where you'll essentially have a sample of cement paste or mortar paste in this device with a known force, a known depth of penetration. You can measure the performance as the cement is setting, right? So you'll perform this test and you'll perform it, you know, at certain intervals of time, and you can plot that and whatnot. We'll talk about that. We'll talk about that next week. We're not going to do a soundness test as a class. Patrick and I will probably, if we have time, try to do a demonstration for you in the lab. But if I ever use the term soundness as it relates to concrete, we're talking about its ability to retain its volume after setting. So how many of you have ever heard of, I'm just curious, somebody's calling me. That's going to have to be a later, I'll have to answer them later. How many of you have ever heard of pre-stressed concrete? Has that term ever popped up? What is pre-stressed concrete? Well, pre-stressed concrete in a nutshell is what happens. So let's talk about concrete in general. Concrete is a material that behaves very, very well in compression, very poorly in tension. So for those of you that have a really, really bad structural analysis professor, concrete would be theoretically great for the members in a truss that are in compression, really bad for the members in tension, okay? The whole notion of reinforced concrete is to put rebar where the tension is, okay? Well, with pre-stressed concrete, oh my goodness.
Answer it.
I'm not answering it. What's that? No, no. Okay. Maybe if he calls again, I'll answer it. I'll pause the video. Oh, goodness. Okay, so let's talk about pre-stressed concrete. So pre-stressed concrete is, okay, so with reinforced concrete, we put rebar where the tension is. But pre-stressed concrete, we take it a little bit of a step further, okay? So what we basically do is we apply a pre-stress to certain tensile elements in the member, namely pre-stressing steel strands. We sort of stretch them really, really hard. We cast concrete around it, and then we let the tension go. And what happens is, by letting it go, imagine that I had a big old rubber band that I stretched. I cast some concrete around it, and I let my hands go. It sucks in compression into the member. Does that make sense? Okay. Now, when we do that, that locks in a compressive force inside the member that can negate some of that tension that you get, and it can make those reinforced concrete beams, if we turn them into pre-stressed beams, they can handle longer spans. They can handle longer spans, they can be thinner elements, etc. Okay? Now, why do I bring up pre-stressed concrete? Because over time, the amount of force that you get when you lock that force in, that force will dissipate over time. And there are a number of sources that will cause that force to dissipate. Okay, one of those sources, for example, is relaxation. How many bass players and guitar players do I have in here? What do you got to do to your guitar strings every now and then? You got to tune them, right? After a while, the force in those guitar strings start to dissipate, so you have to increase that locked-in force inside the string to get to the note, right? That's kind of happening in a reinforced concrete beam or a pre-stressed concrete beam over 30, 40, 50 years, right? Why do I bring this up? Because another reason that that force can dissipate is through what's called shrinkage, okay? Throughout the life of a concrete element, particularly one that's exposed to the outdoors, you will have changes in relative humidity that will cause some of the humidity to dissipate or attract into the element, and that can change the volume of the element. You change the volume of the element, you can change that force. And so that's what's going on here. It's being able to measure the ability of concrete to retain its volume after setting. So you put it in this big old pressure chamber at really high temperatures, really high pressures, and so on and so forth. We might demo that for you if we can. If not, that's it. Okay. This is one of the ones we are going to do next week. In addition to the BiCAP, we are going to cast some mortar cubes. So we have, preset molds for everybody. We'll mix up the mortar, cast it, let it cure for 7 days, and break them. We will do that in the lab. So we get to break something. Yeah, you seem excited about it. We will break some concrete mortar cubes in the lab. We'll be doing a lot of breaking in lab this semester. Okay. All right, so let's see. We'll talk a little bit about water-cement ratio and its impact, and then we'll probably call it for today. So the biggest, one of the biggest parameters that will come into effect when we start doing our mix design is the water-cement ratio. The number of pounds of water to associated pounds of cement, okay? I'll just throw an item out there right now that when we compute water-cement ratios, the cement is going to include any additional cementitious materials that we throw in. So, for example, things like fly ash or microsilica or things like that, that would be accounted for in the water-cement ratio. Typical concrete has a water-cement ratio somewhere between 40% and 70%. One of the things I want to get the message out right now, okay, if you are on a job site and you do what's called a slump test, we'll talk about that later, okay, but a slump test measures the workability of concrete, okay, so you basically fill up a similar like cone, you tamp the concrete, you lift the cone, the concrete will slump. If the slump is very, very low, okay, what that means is you've got a really stiff mix of concrete that's difficult to work with. If you have a job site foreman that says, well, just throw some water into the mix, that'll make it a little bit easier to work with, you tell them to stick their hand out. And you say, no. No. Okay, don't actually do that, but don't do that. Okay? It is a common, knee-jerk reaction that whenever you're working with concrete, if the concrete is too stiff and it's difficult to work with, just throw in a little bit of water and that'll make it easier to work with. And yes, it will. I won't knock that. But as you start increasing the water-cement ratio, and it doesn't matter if you're dealing with air-entrained concrete or non-air-entrained concrete, it doesn't matter. It will cause capillary voids between the cement-water reaction. That will decrease the strength of the concrete. That will decrease the durability of the concrete. That will decrease the bond between layers, the bond between concrete and rebar. It ups the permeability. It is like the worst thing that you could do as a mix designer to fix workability by just throwing a little bit of water in there. It'll be okay. No, okay? Part of the refined procedure that we're going to do is all about correcting for that water, correcting for that moisture, and getting the absolute appropriate amount of water for a given application. So just to throw more water in there, don't do that, okay? We'll probably talk a little bit about types of Portland cement, and then I'll probably call it for today. So, like I said, Portland cement is the most ubiquitous type of cement that we use. We follow ASTM C150 for the production of cement. So when we purchase cement from a supplier and whatnot, and we purchase type 1, type 2, type 3, that's essentially referring to this ASTM standard. And there are 5 types of cement that we predominantly use. I mean, there are others, but these 5 are really the star of the show. We have type 1, type 2, type 3, type 4, type 5. Type 1 is just normal, regular old, everyday cement. That's for most applications, so things like floors, pavements, any reinforced concrete structure. Type 1 cement is going to be good to go. Okay. Now, what about type 2? Type 2 is for moderate sulfate resistance, and so type 2 would be a really good use for an application that's going to be near seawater. So anything where you're erecting, let's say, piers in a bay or retaining walls or big old abutments, moderate type 2 would work very well for there. Okay, type 3 is starting to get to be a little bit more common. Type 3 is high early strength. And so whenever you use type 3 cement, what you're basically trying to do is speed up the construction process. Now, I mean, you know, it's curing faster, but the idea is that with high early strength cement, the concrete will set faster. And so if it sets faster, you can strip the forms off faster. And so you can, if you have a project that needs to be done, type 3 high early strength concrete or high early strength cement might be the way to go. It also helps with the curing time during colder climates and whatnot. Type 4 is what I was talking about with mass concrete. So type 4 is a cement where the heat that you get from the cement water reaction is much more controlled. And so you're going to use type 4 cement when you have a really, really massive structure that you're placing. And a good example of that is a dam, okay? Because dams, you have these really, really large elements, and so controlling the heat of hydration is really, really important. And one way of doing that is to choose your cement. We also have type 5 high sulfate resistance. If you've got a lot of sulfate, you know, near the water, near where it's being cast and whatnot. So like I said, type 3 is becoming a lot more common because of things like accelerated bridge construction, and you could also, if you were using type 3, you could also just replace it with a higher value of type 1. Now, type 1 is the most common. I mean, like probably 90+% of any concrete job is going to use type 1 cement, but I'm just throwing this in there for future use and whatnot. One thing that's about cement, and we'll talk about this probably a little bit more on Thursday, but we often will try and include admixtures or supplementary cementitious materials to sort of reduce the need for cement in our mix. And a common one is fly ash, which actually can be a little bit of a problem in terms of sourcing it. Where do you get fly ash? Anybody know?
Power plants usually, right?
But where does it come from?
Usually coal.
And the production of steel, right?
Yeah.
But we're melting a lot of old steel. We're not producing as much new steel. So where do we get fly ash? You know, so that's a little bit of a sourcing challenge we're starting to see these days. So just random tidbit for you all as future engineers. That is a little bit interesting problem. Like I said, there's all sorts of others of Portland cement. I'm not going to get into the weeds on this, just to know that, I mean, you've got your 5 main types, and there's others and for other specialized applications. One thing I'll say is when it comes to mixing concrete, the use of the water that you use is actually pretty loose. Have you ever heard the term potable water? If you've ever done any concrete work, so potable water is pretty much anything that just barely passes the mark for drinkable. It's pretty gross, if I'm being honest, a lot of times, but you can use it for concrete. You can actually even use seawater for concrete. You just can't really use seawater for reinforced concrete because of the reaction with the salt and the rebar. But if you were casting just like a driveway or some little pad, you know, in your backyard, you could use seawater and it would be fine. You can actually even use non-potable water as long as whatever's in the water isn't gonna affect concrete. Not really a big deal for most concrete jobs around here, but just something worth mentioning. The one thing I will say though, in terms of an environmental issue, is that from the ready-mix plant where they're producing, you know, cement and concrete and whatnot, the wash water from that is actually pretty environmentally hazardous because it's got a ridiculously high pH. It's a very alkaline water, and that's not very good. And so the EPA does have limitations on what you can do with that wash water, so you're prevented from like dumping it at a landfill or dumping it at a job site. Now you can reuse that water for mixing new concrete, that's fine, but you can't just like dump it. Like it's a really, really high pH water, and that's a little bit of an issue. Okay. All right, it's 1:27, and I could get into admixtures now, but I want to like wait on that because there's a lot to discuss about that. There's a lot to discuss about air containers, about Super P, and some other things. And I'd like to wait till Thursday on that. So we're going to pick this lecture up on Thursday. If you give me a couple minutes, I'm going to pack this up. We'll go down and play in the sand. So.